with that. I wasn't good. Yes, now I am. So he started in plasma physics. Now he's moved to the difficult to fathom topic of machine learning. And in some circles, he's well known for the analogy, the song that everyone knows from how's it called? I can't remember. The Holy Grail.
Yeah.
Holy Grail for the Monty Python. So brave Sir Robin who ran away, please show it yours.
Well, I haven't run away yet. Thanks for the introduction. So as DM said, I'm now working in Rome with Luca Bifarale, and our current topic of research, or our greatest focus, is on developing artificial intelligence and data-driven tools for studying complex fluids, both on the side of developing the tools and the data sets for studying them. So this talk is going to be focusing on some research that is still ongoing with Luca, along with our collaborators Antonio Chavani and Massimo Vergasola. And nominally this, while there's little plasma in this talk, nominally this is the theme of the festival is related to control, and this is very much in the spirit of control, at least. So what I'm going to do is, during this talk, I'm going to start with a sort of pedagogical exposition. Start with a pedagogical exposition on Markov decision processes and lay out some control theory with an emphasis on the wrinkle of partial observability, which doesn't get enough attention, with some examples, some of which were curated for this audience. Then I'm going to discuss how you solve Markov decision processes, discuss planning with an emphasis on the contrast between optimal control and these modern model-free techniques of reinforcement learning. And then finally, I'm going to specialize to this recent research on application that I've done, which is inspired by biophysics. So just a brief intro on why I think we should care about these topics. First of all, why should we care about MDPs? Well, they're a very powerful and flexible formalism for nonlinear control and setting up these problems and performing, generally speaking, real-time optimization. And I think this should be a very clear interest to the fusion community, given that we have many things in a tokamak, say, to control. I think the holy grail would be the energy confinement, but there are many other difficult things to control. And we've seen many, I have on the right side, many recent papers that published on this topic using reinforcement learning for various tokamak control things. We have controlling the safety factor profile, controlling disruptions, controlling beta, controlling the ion temperature gradient, and most recently this paper from this year that was published in Nature on controlling the magnetic configuration using deep reinforcement learning. So this is a very active topic of research, and we shouldn't let the experimentalists have all the fun. So a second point is, why should we care about partial observability? Well, the simple point is that the real world is often not so simple that we are able to understand all the, that we have access to a fully observable situation. And whereas most of the literature on Markov decision processes, such as the Bible, Sutton, and Bardo, almost completely ignores this partially observable case. So I'll spend a little time on that. And finally, why should we care about optimal control? I mean, the cynic may say, well, reinforcement learning does everything. It's the future. And while there's some truth to that, I insist that optimal control is a very important theoretical tool and serves as a baseline. And not only that, but it still has direct applications its own place, because for the basic reason that often data collection which is required for reinforcement learning is quite the luxury. And a recent example is that SpaceX, you can say what you will about Elon Musk, but their rockets used optimal control with a model in order to send them into space and back rather than reinforcement learning. Okay, so I have an ambitious number of slides, so let's jump into it. So let me introduce Markov decision processes. Some of this may be reviewed for you, some of it not. So the basic idea is you have an agent and an environment. The agent lives in the environment and interacts with it by taking at each time step an action. And you can formulate this in a continuous way, but I'll stick with discrete during this talk. And so the relevant information about the system is going to be captured by what's called a state. And the state is hypothesized to evolve in a Markovian way, such that the state at one time depends probabilistically on the previous state and the action that is taken. And the cynic again might immediately say, well, a lot of interesting systems are non-Markovian. Why should I care? Well, I mean, this framework can also capture, of course, finite memory by just simply extending the state to, say, k previous time steps. Of course, then this probability may be harder to write down, but that's another issue. And then the final ingredient is a reward, whence the optimization problem, which is administered to the agent at each time step, according again to us in general to some probability that depends on the previous state, the current state, and the action that was taken. And in particular, this reward can and often is less than 0, so that it serves as a penalty that you're trying to avoid. And now the goal, of course, is to craft a policy such that given the current state of the system, you want to choose an action so that over time you maximize the total expected reward conditioned on using that policy, regularized by this factor gamma, which is called a discount factor, which sort of sets how much we care about future rewards as opposed to immediate rewards. So in particular, if gamma is close to 0, then pretty much all the terms in the sum are negligible except the very first one. So we tend to just care about myopic control, whereas if gamma is very close to 1, then we look into far distances into the future. Yes. So you can do either. You can either choose, the policy can either be deterministic, but more in general, you can and often do have a probability distribution over actions. But that was a point that I didn't think would be to be mentioned. But yeah, absolutely, and often it's better to do probabilistically. But it doesn't really change anything from a theoretical point of view. So let me get into some examples. And first, a very simple one, trying to show what kind of problems MDPs describe. So the first one would be a maze, and the state will just be the location of the agent, these white squares, and the agent will start at this square labeled S and try to go to square G. And you take actions, taking you to an adjacent square deterministically. And the idea would be you give a reward at the end for reaching the square G, very simple. This illustrates a couple things. First of all, that in this case, it's absolutely necessary to have gamma less than 1, or else the agent has no incentive to try and reach the target quickly. And moreover, this is an example of a system with a very sparse reward in the sense that only a single state and action pair yields a non-zero reward. And this, I'll say more about this later, it'll become important for our research, but this can often make the problem a lot more difficult. So let's get into a more physicsy example. So the inverted pendulum is a really classic problem in optimal control. So you imagine that you have a cart with an inverted pendulum on the top, and you can have some kind of motor inside with a controller, and you want to apply a voltage at each time step, which induces a force such that we want to keep this angle theta with respect to the vertical as small as possible in as stable a way as possible. And in addition, ideally, we want to minimize the power output as well while we do this. So this motivates what's called, it's a multi-objective reward in the sense that there's multiple terms in it that we simultaneously want to optimize. First of all, the square of this angle, we want to keep as small as possible. We want to keep the theta dot as small as possible so it doesn't start veering around wildly. And then also we want to keep the power output as small as possible. And how much we relatively care about these different objectives is controlled by these tunable constants A and B. And as finally a more inspired and more complicated example is going back to this recent paper in Nature. This basic framework can also be cast into a POMDP. So basically what they did, and this is a little simplified, but what they did was they measured at each time step a number of magnetic fields and magnetic fluxes within the plasma, and then used some simple model, namely Grad-Shafranov, coupled with some assumptions about the heat and particle diffusion in order to infer a current distribution. And for the sake of argument, let's say for the moment that these suffice to capture the entire configuration. And so then at each time step, they take actions which they have a bunch of active control coils within the plasma, and they apply a voltage to it, which induces a control current. And they in their model, they evolve the fielding currents according again to the Grad-Shafranov equation and these assumptions in the heat and particle diffusion coupled with Ohm's law, basically just a generalized Ohm's law. And this defines, you could say, some kind of numerical evolution operator, which sets the probability, again, the state transitions. So now the reward in this problem was extremely complicated multi-objective reward, a combination of many goals, including fixing the plasma currents at certain levels, the position of the last closed flux surface and the position of the X point, and also the value of the triangularity, and many more things with the objective of carefully controlling the magnetic shape. And their claim was this worked. So now let's move away from this this normal fully observable case and move to partially observable Markov decision processes. So if we return to the previous example, you can imagine, okay, so measurements, what if our measurements have some uncertainties associated with them, which, as we know, measurement devices typically do. Say instead, they say for the sake of argument that these uncertainties are Gaussian and uncorrelated, for example. So now we say the system is partially observable in the sense that we don't actually have access to the true states with the true values of the magnetic fields and fluxes and the currents. Instead, the measurements now serve as observations, we say, which supply information about the true states through what's called a likelihood function. So the likelihood of making an observation given the current state and the action taken. And so in this specific example now, the likelihood would be the probability of making a measurement given the true value, which given our choice of uncertainties would be just given by a Gaussian distribution. So then how do you use this? So at each time step, the agent will have a history of all the actions that it's taken and all the observations that it has taken. And the problem is then how do we leverage this information to say as much as we can about the actual state? So thanks to the Markov property, this information can be kind of efficiently captured in what's called a belief, which is simply a probability distribution over all the possible states. And what we do is after each time step after we make an observation, we update the belief using Bayes' theorem, which more or less just comes down to multiplying the previous belief by this likelihood and then normalizing. But a very important point is that doing this demands knowledge of the likelihood, which makes this what's called under the class of model-based approaches to decision making. And this can sometimes be a severe limitation, but we'll talk about this very soon. And so now the problem, analogous to the fully observable case, is we now want a policy that maps the current belief rather than the current state to an action, which maximizes the expected reward conditioned on this belief. And just a couple notes. In the special case of a linear Gaussian model, then this leads to the familiar case of Kalman filtering, or at least some of you may be familiar with it. And also the act of crafting a POMDP policy is also called a controlled hidden Markov model. So let me move into a POMDP, a very classic example of a partially observable decision process, which is that of the K-armed bandit. And this, I'll focus on the Bernoulli bandit case. And so the problem that is posed is that you have K slot machines, and in each time step you can pull one of the K levers. But the slot machines have an unknown set of payout probabilities, each of which may be different, in principle may be different. And so the problem, of course, is to ask which sequence of levers you should pull in order to maximize the total discounted reward over time. Here is another case where the discount is very important because it sets up a competition or a trade-off between actions which tend to gear towards exploration, which is discovering the unknown probabilities, and exploitation, which is to use the information we have about the probabilities to try to reap rewards as quickly as possible. And depending on gamma, this will set which one of these we care more about. So this problem can be cast as unsurprisingly as a POMDP, although that's not the only way to cast it. And so as a POMDP, the state is simply the set of the probabilities, which in this case have a trivial transition matrix. It's just because it's static. And the actions are simply to pull one of the levers, and the observations that we make are the rewards that we reap when we pull the lever, which can, in the most simplistic case, can be just 0 or 1, and the likelihoods are just set by these probabilities. And so in this particular example, we have the interesting fact that the optimal policy can be specified exactly due to a classical result of Gittins from 1974, but usually this is not possible, and we have to resort to more general methods, which leads us to the Bellman equation. So first, you define a value function, v pi of b, which is the total expected reward under your policy pi conditioned on your belief, which has this expression. And it's quite easy to show that the optimal value function in general satisfies this Bellman equation, which is a nonlinear functional equation, but its statement is very simple, which is that the value is really just, yes, is really just a sum of the value of the immediate expected reward for taking the action one time step in the future, and then the contribution from all future expected rewards. So in principle, it's easy to imagine that this equation can be ungeneralized back to the fully observable case, where it's basically just all these probabilities and beliefs become delta functions. And in principle, it can be solved exactly in all cases using dynamic programming, but especially in the case of partial observability, the solution can be very hard computationally. And the reason is that the value function is a function of the belief, and the belief lives in a large simplex, which has dimension equal to the number of states minus 1, and if a problem is with 100 or more states, this can quickly get out of hand, and you have to be able to specify the value function on this entire simplex. And this is called the recursive dimensionality. And I don't really want to spend too much time on the slide, but suffice it to say that we do have approximation methods which are able to compute an approximate value function for a given POMDP, basically using iteration on the Bellman equation. And once you have the optimal value function, it's basically trivial to specify the optimal policy, because you just act greedily with respect to that value function. So I've talked now a bit about, this is the paradigm of optimal control using the Bellman equation. So in contrast, there's reinforcement learning. I'm sure you've all heard lots of stories about reinforcement learning. It's been used to solve chess and find really good and Go and whatnot. So it really is a powerful approach, and it's extremely flexible, especially because it's model free. And you do not actually need to know the underlying state dynamics in principle, or even the reward structure. And the basic idea is that you iteratively learn a policy by exploring your environment over and over again, and logging the reward and noting the states that are observed. And then you just continually increment your policy as you move along. And in the process, you can in principle discover the hidden state dynamics in the reward structure just through the observation. And so one illustrative paradigm of this is Q learning. So it's a slight generalization of the value function is the Q function, which is now the value of taking the action, a given action under a given state, which suffices to specify both the value function and the optimal policy. And so what you do in Q learning is that each time step you update Q according to, or maybe it could be many time steps, you update Q according to this equation here. And the basic point is you take your old Q and you add a term which expresses basically the difference between the current Q and the Bellman equation, which Q satisfies. And so that this equation goes, so this term that's proportional to alpha goes to 0 when Q is optimal. and alpha is called the learning rate here. And in modern algorithms, Q we usually represent with a deep neural network because it could be a very complicated function principle, and neural networks are very good at approximating arbitrarily complex functions. But of course, reinforcement learning is not always very easy to use, even though you could argue very well that it's probably the future of control. And there's several reasons for this. First of all, there's no one-size-fits-all approach because we have a number of different Q-learning algorithms at our disposal, some of which may be good for one problem and bad for another. These include, in addition to Q-learning, policy gradient methods, actor critic methods, and a whole zoology of them. And moreover, we also, for every given algorithm, there's a whole mess of hyperparameters which often need to be carefully optimized for a given problem in order to obtain a good solution quickly. And on top of this, we tend to need oodles and oodles of training data, which may be very expensive to gather, and it may take, in the end, a lot of time to obtain a good policy that's converged. And finally, while reinforcement learning is in principle model-free, this can come at a price, especially in hard problems, that may contain long-term memory and dependencies between the states and sparse rewards. And the problem that I'm going to talk about very soon, just one more slide, is an example of this, where POMDP is actually easier to apply. And so just to summarize the contrast between these optimal control paradigms and reinforcement learning is that on this graph, where on one axis we have the information that we're able to perceive about the state, and on the other axis we have the knowledge that we have about the environment, about the model dynamics. So in the upper right corner, we have the idealized situation where we know everything, and then we can use classical optimal control and MDP. If we relax the information that we have about the state, we move into the realm of POMDP. And then finally, reinforcement learning can in principle do everything, but there are drawbacks to everything. MDPs and POMDPs can be computationally hard to compute, and reinforcement learning also can take a lot of time to solve, but on top needs oodles and oodles of training data and lots of hyperparameter optimization. Okay, so let's finally move into some research. So this problem is biologically inspired by the observation that in nature, many flying insects depend on a remarkable ability to find the sources of odors or other cues which are convected by the atmospheric wind. A very annoying and familiar example of this is mosquitoes are very good at finding tasty humans, given the CO2 that we breathe, and in addition to another bouquet of odors and heat that we give off. Another example that's well studied in the literature is that of moths searching for mates. Male moths are very exquisitely attuned to sex pheromones emitted by females, and they're capable of searching for the moths and finding them upwind on scales up to and exceeding 100 meters. So this is a really fantastic ability to navigate these turbulent environments. And this is a plot showing a real trajectory from a real moth from an experiment that was published in 1983. And you can see that it's following kind of a crazy zigzaggy pattern. You see some features that are very generic to how they do the searches, like they have these periods where they're moving crosswind and then interspersed with periods where they're moving upwind. And these are respectively called known as casting and surging. So the question is, so how do they do this? How are they able to locate the source? So the immediate first guess would be, okay, they use some kind of gradient estimation. If the concentration field is sufficiently smooth, then given a couple successive observations, you can get a local estimate of the concentration gradient and then simply just try to move up the gradient. So this works for bacteria, but it does not work for moths because of the long length scales that we're on which the advection of passive scalars is dominated by turbulent transport. And the result of the turbulent transport is that it mixes the Q into a highly intermittent pattern where you have patches and plumes of relatively high concentration interspersed over a background of essentially zero concentration. And as a result, the tendency will be that an insect will only detect the Q intermittently, and it can go long times without detecting the Q at all. It could be 10 seconds. And so in particular, this strategy of gradient estimation is completely unfeasible for this problem, or at least very impractical. So here's a couple plots from experiments illustrating this more explicitly. So on the right-hand side, we have a plot of the concentration signal from at a fixed location, 50 meters downwind from the source. And the point to highlight is that we have these long periods, again, of very, very little concentration interspersed with these spikes. And you can imagine this kind of spiky intermittent signal is what the insect will see as it searches. And as we can quantify this a little from using some theoretical approaches, you can calculate that under appropriate conditions, the PDF of time between successive whiffs of the signal tends to go as t to the minus 3/2, which has been validated by certain simulations and experiments. So this sets up the motivation for the problem. So how are insects able to perform this search given that their Q detection is intermittent? How do they leverage this kind of limited information that they're able to glean? And so what kind of strategies work well? Can we say anything about the optimal strategy, and how do well-known heuristics for this problem compare to the optimal strategy? And so what we do is we cast this problem in as a POMDP, and by now you're experts, so I probably may not be surprising that we can do this. The point, of course, is that we can't observe, the agent doesn't know where the source is, so this makes it a partially observable problem. So what we set up was we have a two-dimensional grid world on which the agent lives. We have a large rate in particular with over 3,000 points. And at each time step, the agent moves into an adjacent grid point deterministically and makes an observation of either a hit or a blank, either a detection of the Q or no detection with some specified probability. And of course, the goal is to try to find the unknown source location as few time steps as possible, which is modeled by we give a reward at the time which it finds the source. That is gamma to the t for reaching the source in t steps, where gamma again is a discount factor, which we generally try to keep as close to 1 as we can. So now the key physics input into this problem, of course, is the probability of making the observation given your relative position with respect to the source, which acts as a state. And this is a difficult and interesting physics problem, which some work has been done on it, with characterizing the spatial dependence of concentration statistics in a turbulent environment with or without a wind. But to be clear, we use a wind in our model, but in this work we use a very simple, arguably. Sorry, yes.
I wonder whether the strategy can change when there's no clear direction of the wind.
Oh, absolutely. I mean, it's a completely different problem with and about the wind. Here we assume that the agent can observe the wind and its direction and its magnitude, which I think is one of the less egregious assumptions that we're able to make, because I think wind is quite detectable in the real world. But absolutely, if you turn off the wind, it becomes isotropic. You probably wouldn't observe as much casting, because if casting up and tries, it can be seen as a strategy to try to find the symmetry axis of with respect to the wind. That makes sense.
What do you assume about the wind in terms of ratio of
Uniform.
and constant in time?
Yes, it's a big assumption. I mean, but this is a hard problem to begin with. Yeah, I mean, you can think of all kinds of
constant in space.
Yeah, constant in space, but I mean, you have, but now what you add is you add a turbulent diffusion, which you can take as large as you want. Yeah, you can say that, and well, this is stupid, unrealistic, and I fully agree. But really, what this captures, the important part that it captures is you have a non-trivial distribution of concentration, and in particular, if you tune the parameters in such a way, in an appropriate way, then the probability of making a detection is quite small. In this plot, it's between 10, less than 10% typically, as small as 1%. So you're going to have, So this captures really the hard part of this problem, which is this intermittent detections. I mean, of course, we could replace this with a more realistic model, provided that you don't have the correlations between detections, which is a whole nother ballgame that we're thinking about for the future. So now what we do here is we just impose a mean wind with an effective turbulent diffusion and fix a point source, say at the origin, and then so you obtain the stationary solution for the concentration, make a simple assumption about the number of detections that you expect per unit time, and this could be turned into a detection rate, and the final assumption is that the number of detections in a unit time is treated as a Poisson process, and we define a detection as any number, or an observation as any number of detections within exceeding one, greater than equal to one within a time window. So whence we get this expression for the probability of observation. So here are some heuristic strategies that have been proposed for solving this problem. I mean, what we're going to do is use a near optimal policy using this algorithm that I mentioned briefly in the first half of the talk, which is called Perseus. But it's important to compare to some well-known heuristics and also the benchmark against them. So first one is POMDP, which in this case is basically taking the action which minimizes the expected distance to the source. So this is an example of an exploitative or greedy policy because you're trying to immediately use the information that you have about the source to try to strike towards it. In contrast, there's infotaxis, which was introduced by Massimo and others in 2007, which is to take the action which maximizes instead the expected gain in information as measured by the entropy of your belief. And this is, of course, a more explorative policy because you're just you're directly trying to gather information. And so it's very natural then to try to interpolate basically between these two approaches, which leads us to a recently introduced policy called space-aware infotaxis, which is basically take an action which minimizes a function which depends on both the distance and the entropy. Yes? I mean, based on these approaches, as it relates to these approaches, not really. I mean, the simplest heuristic, which is based on real observations of moths, is called cast and surge, which is really just a rule that after you make an observation, basically you start moving upwind, and after in the longer time that passes, you start moving back and forth in the crosswind direction. But this isn't. It doesn't really work in a strict sense because you're probably going to miss the source every time, even if you come relatively close to it. So these are more formal strategies, and while it's hard to relate precisely what they're doing in the real world, we observe that we'll see that a lot of kind of trajectories and behaviors that mimic what's seen in the real world kind of are emergent somehow. One thing that we do know is that the insects do use the correlations between observations. This has been established pretty much without a doubt an experiment, which is an unfortunate point for this kind of Markovian approach. And again, I'll say a little more about that at the end. Okay, and a final heuristic strategy that we use is called Thompson sampling, which is another explorative kind of policy, because what we do is we now sample randomly a point which we think might be somewhere where the source is from your belief, and then you move towards that point until you either reach it or until a fixed number of time steps expires, and then you repeat and resample. That's actually a good question, and unfortunately, I'm not sure I have a good answer for that. I mean, maybe we have some more promiscuous moths and some more moths that are. No, I think if I'm not mistaken, we have had experiments where we have just a single moth that's emitted cues, say in a jet flow or like a wind tunnel, and then we have a moth searching for it, and so they can't rely on there being a whole bath an ensemble of moths for them to find. We do know that one point that's interesting, or maybe simplifies this a bit, is both moths and mosquitoes, once they get sufficiently close to the source, they do start using, say, visual cues to aid in their search. But this is, of course, possible on these long length scales of 10, 100 meters. Yes? Yes? Oh, no, keep going. Okay, so sorry. So one quick point for solving for an optimal policy. As I mentioned before, having a sparse reward structure makes the problem pretty hard because you only give a reward when you find a source, and this can lead to problems with convergence. So a really important point that we discovered in order to get a good policy was a trick called reward shaping, in particular potential reward shaping. And so the idea of reward shaping is that we're exploiting a hidden symmetry in the problem, which is that if you write down your Q function as the expected value of your belief and an action pair, then we can add an arbitrary function which depends only on the belief without changing the optimal policy. And so this kind of leads to a gauge freedom in choosing a reward, where we can add any function of the following form, where phi is a state-dependent function without changing the optimal policy, which can rectify this sparsity problem. So a good choice can really accelerate your convergence. In this problem, we generally want our phi to be increasing with the distance to the source, which in practice basically yields a small reward for moving closer to the source, but in a careful way that doesn't change the optimal policy. And just to quickly illustrate that this really makes a difference, this is the performance of the policy as a function of iteration for many choices of the shaping. And the main point is that this brown curve is the unshaped case, and it's taking many iterations to get to this black line, which is the best heuristic baseline. But once you turn with a good choice of shaping, for example, this red curve, it only takes 4, 5, 6 iterations before we're comfortably beating the best heuristic, and it's pretty well converged. Yes.
In some strategies, even when you find the solution, you
so this is a convergence issue. So I mean, so Perseus is an iterative algorithm where we're constructing a value function that gets, in principle, successively better and better from iteration to iteration. But I mean, what we see is that this is in practice cannot be the case. Doesn't really come with guarantees of convergence. So again, there's some hyperparameter tuning that's involved. I mean, in this case, it can be extreme because we found that depending on the choice of shaping, if they say the coefficient in front is too small, it leads to stability issues, which we don't entirely understand at a fine-grained level, but it's kind of like it's analogous to having a momentum that's too large, is how we see it. Okay, so I have a video, but it didn't properly embed into my PDF, so I have to change my software real quick. I don't know if the screen sharing is going to work, but so this is a video of some trajectories that are obtained using the optimal policy from the same fixed point, which really illustrates the variance intrinsic to the kinds of trajectories that you can get. Basically, I ran 21, ran it 21 times and took the best one right in the middle and the slowest one. I'll do it again. And these black circles are the detection events. So what's the point? The point is that, well, I don't know. The point is that we can see a variety of behaviors that emerge from this, including this kind of tendency to combine this upwind motion with this crosswind motion. And it contrasts with what you see in heuristics. We see a whole zoo of other kinds of behaviors. I don't have a video for this, sorry. So QMDP, as we said, but this was an exploitative policy, and it tends to try to dash towards the source, and in practice, it kind of gets stuck. for arbitrarily long times, infotaxis and Thomson sampling for these more meandering trajectories consistent with there being explorative policies. And finally, this one that I said was in the middle is actually very close to the optimal policy in terms of the probability of taking the same action. And this slide just shows that we claimed that we're actually there's a near optimal policy, and thus it should actually be beating all the heuristics that we test in terms of the arrival time. And this is just confirming this on 3 different choices of the emission rate and on 5 different test problems. These blue stars are the near optimal policies, and in every single case we're comfortably beating the heuristics. And if we can be a little more detailed by looking at the arrival time PDFs. So this is for the lowest emission rate case. So the point is that the blue curve, which is Perseus, it's the best. In this case, Thomson sampling we find is doing very well, and the shape of the PDF is very similar. But in contrast, this orange curve, which is this exploitative QMDP, just doesn't work very well. You can see that it has a really fat tail, which really shows the downside of trying to be too exploitative when you have limited information. And then you can start cranking up the emission rate, and now a different policy heuristic is the best one, and it's that space-aware infotaxis I talked about. And then finally, it's not till you really crank up the emission rate that the QMDP starts being a reasonable policy, and its fat tail starts disappearing. Okay, one final remark is that kind of illustrating the downside of having, one of the downsides of this model-based approach is that you can kind of lead to overtraining in the sense that if you relax the assumption that the model that the agent has is perfectly describes the model, then it can start to perform poorly. So here the agent is searching an environment where the parameters are actually different from what we trained it with and what we update the belief with. And what we see is now the so-called optimal policies is doing quite poor and has a really fat tail for the arrival time. Whereas now finally the infotaxis, which was vanilla infotaxis was kind of mediocre in these other cases because maybe it's a little too safe. In this case, it's actually doing quite well and has the best mean arrival time because there's a tendency towards exploration and safety. And so I should probably wrap up and just talk about some future directions we want to go with this. So first of all, I mean, part of the point of trying to get these optimal policies on big problems is that we want to study more complex search problems, such as those involving multiple sources and multiple queues, or dare I say, moving to 3 dimensions. I mentioned kind of qualitatively, you can see that there are different behaviors emerging from these different policies, but this hasn't been really addressed in a careful quantitative way. So this is something that we've started looking into. What we started doing right now, in addition, is we're building up DNS of a point source with a mean wind, and we want to see how these policies now perform in a real turbulent flows. And really a salient point here, again, is it's going to be really hard to ignore now the correlations between detection events. Because as we know, real flows are correlated and real insects actually use these information. So this is a difficult problem. We have some thoughts about it, but it's a little too early to share. All right, well, thank you for your attention.
Time for one or two questions.
Well, so I mean, I guess that's a good point. I mean, it depends on what your criterion is for best, which isn't really well defined. I mean, you can imagine maybe a real insect cares more about the peak of the distribution rather than the tail. But I mean, what we were measuring this by was the mean arrival time, which is dominated in this case by the tail. So yeah, it would be the ensemble average of the arrival time. Right.
So it isn't clear to me how much of a bonus you get in performance for having a better physics model of the turbulence, the turbulent transport and mixing. And one could think of raising, you have this large system. I mean, I would argue that you should be representing the larger scales, and the scales of the system is kind of a random but correlated, of course. And the smaller scales is a diffusion, blah, blah, blah. But, in other words, does better physics lead to better performance, and what's the increment?
So, I mean, in this toy problem, it's a non-issue because we're really exploring kind of in a narrow way solving a specific intermittent surge problem for a specific model. But when you start to move to a real turbulent flow, this really becomes a pretty poorly understood point. Now, what model features are important? My expectation is maybe that these small scales aren't so important. But I mean, the honest question is, I don't know. And that we're going to be carefully studying this very soon in the future. Right. So there are people that work on this. This is called multi-agent reinforcement learning. And it is an interesting problem. I think some work was done where just using infotaxis, the claim was, I think, that you see like an improvement in the arrival time that scales as like something like 1/n, where n is the number of agents. So you really do see a benefit in performance when the different insects can watch each other and follow each other. But this can't really be efficiently captured in the kind of POMDP framework, because with each agent you increase the state space like pretty astronomically, because and which really you just run out of memory and run out of computational power. But no, it's an interesting point. It's studied in the literature. This is kind of a separate problem.
The framework of the Arcturian processes. There is some change after the result according to how long is the memory of the
Right. So we go back to this first slide. So the most simplistic approach was that you just simply have your state captures the information in the current time step, and then you have a transition from the previous state to the current one. And I mentioned that you can extend the state to multiple time steps. And yes, both the size of the time step matters and the number of time steps that you're trying to capture. And of course, the problem gets harder the longer time memory you want to include. But yes, certainly, if your time scale is too short, your time scale is too long, and you certainly miss important dynamics of your time step. If your memory and you have to tune the length of the memory to the intrinsic memory of the problem. So yes, both of these things are important.
Maybe a short one on that one. We have a correlation between how far back you go in memory and how efficient the infotaxis becomes, right? Because gathering information in order to make some action is probably directly connected as well to your mind.
Right. I mean, and when you mention infotaxis, I mean, it kind of sidesteps this approach of trying to explicitly encode the memory by using this sort of Bayesian inference scheme. So rather than have a collection of independent states, you use you have a belief. I'm sorry. What was another component of your question? Yeah. Okay.
Yes, I know there are other questions. Let's go for answer. Thank you very much, brother.